Hi, this is Jose Sanchez, and this is lab lab 4, the ansys project. First, what I did, I went to geometry to set up the new measurements for the horizontal plate. As we can see here, the dimensions exactly as specified, everything in inches, 9.005, and the height of this, and then I locked it in the structure and put it on the same wind tunnel. After I put in those measurements, we went to mesh, which mesh, what I did was basically obviously name every single feature here. And then I meshed specifically the outside with triangle right here, one body, the main body, and geometry. With geometry means I just press the image for it. Now for body sizing, I selected only the vertical rectangle in the middle. And I pressed it to measure specifically this part of the object and have more precise measurements here. Then I selected what values I think were reasonable, right? And I think I put right here 0.03 for the element size. When we meshed it, we have this we have this mesh generated one. Here it is. Here's how it's meshed. Wow, the structure perfectly. Now we're gonna go to Fluent. After we got a Fluent, we started selecting what parameters were adequate for the experiment. We put the basics for air, the density of air. Then we went to boundary layers, so we could put the initial velocity of 10 hertz, which is exactly 1.617. Perfect. Then we did outlet, which was basically only the pressure of the outside, which that's it's the basically the pressure of air on sea level. Now we go to reference values, right? Because we're gonna update that as well as the initial velocity of the inlet. There's basically what our values are going to be referencing on, which is basically the pressure at sea level outside, which is 101,325, and the velocity of the wind tunnel. After that, we reported some definitions which the experimenter told us about, which were the lift coefficient, right, which we're going to compute. And then we also going to do the drag coefficient, which we're also going to compute. After that, we obviously initialized. After we initialized, the parameters that I put were 100 instead of 30, so it took a little longer. Here you can see the initialization, which I go up a little bit more, which was here, initialized, then to get the residual plots and stuff. Right here was the first attempt, and here's the second initialization, which was 100. Perfect. Like that, so you stop here. Uh, Now we're gonna run calculations, right? I put 250, which right here you can see iterated for 250 values, right? After that, we already did all the converging, all the meshing, and the geometry of the shape that we wanted. We wanted then velocity contours, which we can see in display right now, which already calculated. And here is the velocity contours. As you can see, it kind of lifts a little bit here. That's kind of a little bit of the boundary layers, a little bit. You can see them right here. Not really because it's velocity contour, but you can see kind of like how it looks like. Uh, yes, and after that, then we went to the to see what was the let me see here. We want to see the perfect right here. Okay, so let's remember the boundary layer thickness. There's three locations for both numerical simulation experimental using boundary layers, velocity to the layer velocity profiles, right? So what happens here? We went directly to this graph, and we first had to indicate where were the positions. For example, first point right here, as you can see right here. One second. Let me repeat. Okay. As you can see, I had to do a little bit of computing because in this case, the geometry it starts at zero, right? So then how far are we? How far away are we? So we are now at zero here, and we have to find out what was the first position that we wanted to find out, right? Which in this case, my calculation told me that it was going to be 0.113 inches to the right. Remember, this is in meters, so I had to change everything to meters and collect it at zero. So it's zero from this endpoint. From this endpoint, we'll go back to the geometry. So basically, from this endpoint to the center, it's 45. It's 45. So now, from this end, from the inlet to the middle of the geometry, it's 45 plus half of this bar. Now, this half of this bar is going to be the value that we want minus 2 centimeters away. So that's what we see here on the calculations, which is exactly 2 centimeters after the graph. Then we have 8 centimeters, which is 3.115 inches away. And then you have a third one, which is before the center point. As you can see, I could see the second one right here, right, which is 0.07 meters away from the center, and then you have the third point, which is negative 0.0445 meters away from the exact center. Now I'm putting this just so I could have a coordinate. So I'm gonna have a coordinate here at negative 0.045, right? On zero, and then I'm gonna have one above it, one above it. So I'm gonna have this. I'm gonna have like a little line here, and then I put cut, and I sampled exactly one line for each of them. So I could have a good reference point of where I'm looking at this. Now for the graphs. For the graphs, basically, I I plugged in the first point, right? The first point is specifically for the velocity and y-axis, just to have a reference of what is it doing in meters. So basically, this what is happening for the velocity here. So I have a velocity going right as soon as the meters increased, and there's the two reference instrument values of each. Here you have one of them, a second one right here, right, and then you have a third one right here, which are pretty similar. Which are pretty similar. Now, Now we went back to Fluent because now what we needed was the skin friction. We needed now the shear stress and local skin friction coefficient, right? And also the drag force coefficient. So let's start with wall shear stress. Let's go to the Fluent answers now, right? And we're gonna go to graph plots right here. And this graph, basically, you're gonna put wall flux and you're gonna specify, you can specify, let's say in this case, we want wall shear stress, right? And we're gonna select only the plate because the plate is the one that you want the shear stress on. So you're gonna select it, and here you have a graph for the shear stress. Now, if we wanted, let's per se, skin friction, right? We're gonna display the skin friction, and here you have the skin friction as well. That's so you get both graphs for both of them. You could also probably like change the graph of how it looks like. Probably gonna do that for the um for the lab report so it can look nicer. But yeah, this how you get these two values. And for the last thing, we are going to get the report definitions, right? So let's say we report definition, lift coefficient, right? We compute. So basically, this is the lift coefficient of the plate. Perfect. And now let's say we want to calculate the drag coefficient. That's what the problem asks for, and this is the drag coefficient of the plate. And that's how you get all your values for this project. You started with a basic of like geometry, right? Then you messed your object like every single time, so we could have a good calculations of everything. We went to Fluent, we got the variables that we wanted, we initialized it, we find the we then compute it as residuals so it diverts into a number that is fit for our calculations that we have already determined what it should look like. Then we graph the skin friction coefficient, we graph the wall shear stress, right? And at the end, also, we went here to calculate the velocity on the graph for each of the points that it was specified at different distance along the plane. Thank you.